So this is a simple harmonic motion or a wave motion demonstration and experiment for elementary physics. And we're going to work through this using this video and then follow up with some simulations and calculations to make up the lab for physics. So in front of you is a string. On the far left, there's a weight which pulls on the string and puts a tension in it. And then on the right, there's a little vibrator. And we're going to take a close look at each of these, and I'll show you how they work. And then we'll turn it on and change the frequencies and the tension to adjust to see different modes of the string vibrating. Later on, we'll come back and look at some of these things in detail in a separate lab experiment. So the unit in the center of the picture here is a vibrator. It's actually just a part of a speaker. You can see it down here at the bottom. This is the part that would vibrate to make sound in a normal acoustic speaker. There's a little plunger attached to it which can move up and down. And when it goes up and down, it makes the string go up and down, and that'll set vibrations in the string. The string is clamped here to that. It's also held over here in case it comes loose. We'll need to measure the properties of the string separately, but for now, what we're interested in is the frequency of vibration. And that's set by this little sine wave generator, which is electrically run and claims to know what frequency it's running at. So if I turn it on, so I can figure out how to do that, then we should be able to make this vibrate. So the sine wave generator has a little on-off switch on it here, and I'll just turn that on and you'll see it come alive. That's the frequency in hertz or cycles per second that's being delivered through these two wires to power the magnet which moves this up and down. And I can change that frequency by steps of 1, like that. I can also change how strong it is, the amplitude of vibration, which is how much this is moving. You can see this move in the video here, and I put my finger on it, it vibrates my finger. So that's running right now at 100 hertz, and we're just going to let that run like that. So that moves this up and down, it vibrates the string, and now the string is moving up and down at this point at its maximum amplitude. And that amplitude is set by how much we change this. So I can make that pretty small, or I can make it pretty large, like that. Okay. So now the string is vibrating, and as we go along the string to the other end, we'll see the weight on the other end applies the tension which controls how that string sets up waves. Now at this end, the string comes over a pulley, and there's a weight hanger and masses on that, so that these masses, with the force of gravity, apply force on that string, which translates across the top of this pulley. The force down here is the same as the force which is in the string, which we would call the tension in the string. There's a weight holder and 3 weights. Each of these weights is 100 grams, and then the weight holder we previously measured in another experiment. So the more force here, the more tension there is in the string. You can see the effect of that if I just add a little extra here with my hand. So we're going to just leave this at 300 and about 350, counting that weight hanger, and that's the tension in the string here. And then we're going to look at how the string vibrates while we do that. This is a close-up view of the string. The camera's focused on the string, so it should be fairly sharp for you to see. That point right there that's not moving is the key to trying to understand how these waves work in the string. Here the amplitude is greatest, here it's least, over here it's least again. There are several of these spots along the string at which no motion appears to occur, and between them are spots where the motion is greatest. Now we're looking at the end of the string over the top of the pulley, and you see that it's not moving here. So we call a point that doesn't move a node, and a place where it's moving the most an antinode. There's a node here, there's one over here, and on down the string like that. So there's one here and one there. So now the vibrator is moving the string up and down at this point. There's a node here on the tension side of the place where that string is clamped. If we look down the string, we'll see other nodes down the string. There's one here, there's one there, there's one here, there's one here, there's one there. Put your finger right where there's a node, it will not disturb things too much. If you put the finger over here where there's an antinode, then it makes the string vibrate up and down even more. And then it stabilizes. So the reason there are nodes and antinodes is that there's a standing wave on this string. There's a wave going one way and a wave going the other way. And the two waves add and cancel out at the nodes. So the net motion there is 0. And the greatest amplitude is between the nodes. So we can count the number of nodes to determine the wavelength, or we can directly measure the separation of the nodes just by putting a ruler or a meter stick underneath it to see how far apart they are. So the string is vibrating at 100 hertz. We have 3 100-gram weights on one end, plus the weight of the weight hanger, which is about 50 grams. And you can see nodes in the string. There's one right there. A little bit hard to define it exactly, but it's right about there. There's one over here, and there's one over here. And from the perspective of the camera, you can get a fairly reasonable measurement of the spacing between these nodes at this frequency. So the meter stick is just a few centimeters behind the string, and the camera's far enough away that there's not a lot of parallax. That'll be reasonably accurate. Now I've changed the frequency of the sine wave generator just slightly, and right now it's 97. If I make it 96, 95, 94, 93. It changes the resonance, which sets up this standing wave. So I'm not going to get it exactly right, but somewhere right in here at 97, I can make small adjustments. That's 96.4. Makes it pretty stable and easy to see the standing wave pattern. Now you can see the nodes very cleanly. There's one right here, there's one right there, and one over here. So that you can measure the separation of the nodes in this video. And the frequency at this point is 96.4. Just tuned up a little bit from what we started with to make the waves stand out really cleanly. Now I've removed one of the weights, so we have 200 grams plus the weight of the weight hanger, creating the tension in the string now. And the frequency at which this resonates to create that pattern is 81.4. So again, you have a node here, and a node there, one over here, and one to the right. You're able to see at least 2 nodes in this video. Now things are exactly the same as they were before, except I've reduced the frequency of vibration. So right now it's 44.4 hertz. There's a node on the left at about 76 centimeters. There's a node just out of your view, which I'll pan over so you can see it, over here. And if you stand straight in front of it, it's at about 124 centimeters. There's one over on the far left over here. You can just see, I'll put my finger where it is. It's at about 27 centimeters. So we have 27 and then 75. And then one over here at 120 something, 24, 25, somewhere around that. And that's for a frequency of 44.4 hertz. So now if I try to decrease the frequency again, let's see what happens. That frequency is 26.4. And you can see a node just over here at my right at 142. So I can make that a little clearer for you. And then over here on the left, past the Antinode, and then we'll get to another node over here on the left. Right about there, which is at about 62. Maximum amplitude is pretty much in front of the camera. So if I can zoom out so you can see the whole scene. And then the vibrator on the right. And the weight hanger on the left. And this very long standing wave in front of you, running from about 60 on the left to 140 on the right. This one right there measures almost exactly 142, give or take a centimeter. And the one over here on the left measures about 61. Or maybe 62. There's a region where you really can't tell, right in there, where it seems not to move at all. And that's for a frequency of 26.4. So I'm going to go from here, I will go up now, and we'll see what happens. That's 35.4. And we have a node here at about 99, and one over here on the right at about 159 and 160. And this is around 42.4. Adjusted it a little bit, it's 44.4. So here we have a node at 123 and a node over here at about 74, 75. About 64.4. Not real stable, but you can see some notes. a note here at 112. There's one over here at 145. There's one on the left at about 78. 64, and then on the left notch. We have nodes at 68, about 97, 127, 156. We've got one on the left. 59. This is around 85. That's about 110, 136, about 162. It's about 90.7. Now we have those at 52. 75, about 97, 121, 144, and about 168 over here on the right. Now we're at 100.7. I'll just read the nodes off. It's not real stable, but it's good enough. So about 2 centimeters, 23.5, 44, 64 or 65, about 85. And then on the right, about 107, 127, 149, and one over here at around 169, and then another one out here at 191. We could even go higher, but it's about 110. You can see several nodes for yourself because the video frame is big enough to see at least 3 or 4. So the higher the frequency, the more nodes. The lower the frequency, the bigger the spacing between the nodes and the fewer nodes from one end to the other. This is for a mass loading that string with a tension. The mass has 100 gram weights plus the 50 gram weights, providing the tension in the string is being driven by this oscillator. Now the other thing that you'll need in order to be able to figure out what's going on here is the length of the string from the place where it passes over the top of the pulley to the place where it's clamped by the vibrator on the right. And we have a 2 meter long stick here to make that measurement. I'm just going to hold it up, you can see, and then I'll tell you what the answer is, because you just need that number. So we just put it up here at that end, roughly at the place where it rides over the top of the pulley. And I'll just try to set it here so it won't move too far from that spot. And then at the other end, we need to measure where it is at the place where it grabs that string with the vibrator. This is the end of the 2 meter stick right there. So we just need to place a mark there. I'll just use the end of my finger, and I'll just run the stick over to get a measurement. It doesn't have to be very accurate to do this well, because the uncertainty in those nodes is several centimeters. So that's, with that there, my finger is at 168, the end of the stick is at 2 meters. So we have 10, 20, 33, centimeters plus 2 meters to get the total length of the string that we're dealing with in this experiment. This is the pan balance that we have used in other experiments in this lab, and we need to measure the mass of the string to actually get the mass per unit length of the string. So this is the same type of string which was used in the experiment. It's not the same string, but it's representative. So we'll just drop it on the pan balance. It's balanced right now at 0. I'll just put the string on there. You see it goes out of balance. And then we'll see how much that string weighs by adding mass on this side until it balances out again. So right now we're at 2.5 grams. And that's about 2.8 grams. So the mass of that string is 2.8 grams, and then we'll need its length, which I'll get so you can get the mass per unit length. So now you see the string at the end of the 2-meter stick on the left side here. And there's a loop and a knot there, which you'll have to estimate how much string is in that. Then we'll go to the right side. Now you can see the other end of that string that we just measured the mass of. For the most part, you could probably even ignore the extra string in that loop, but if you want to be extra accurate about this, you could estimate how much is in the loop of the knot to try to account for that to get the total mass per unit length of the string. You'll need that because the string in the experiment, the effect of the tension on that string alters the speed of the wave, and that, to find that, you'll need the mass of the string.